Hi. Some students requested to discuss about stereographic projections and branch points and several other things. So I thought I should talk about them. So stereographic projection is something familiar to all of you. The idea is that we are supposed to adjoin the symbol infinity, the point at infinity to the complex plane, and consider the extended complex plane. So in the real case, we are doing the same, but there you have two infinities. I mean, plus infinity and minus infinity. So when you go to the along the positive real axis, the right side, it tends to plus infinity, and similarly, you know how it goes to minus infinity. But unlike the real case, in complex analysis, you have only one infinity. In fact, it is just like the one-point compactification. So how do you make sense of this? So let us come to this. So you adjoin a point at infinity, and you define the algebra rules in the typical way. And how do you geometrically make sense of this? So the extended complex plane you denote it by C hat, and what we do basically, we identify the extended complex plane as the unit sphere. So let us see how we can do this. So you consider the unit sphere, and what you do, you send the north pole, that means the point 0, 0, 1 to the point at infinity, and the remaining term you define a map in this way. x1, x2, x3 goes to x1 plus ix2 by 1 minus x3. In fact, what we are doing here, so I will show you the picture. So you draw a line from the north pole, and you view the complex plane as is passed below the means in between the sphere. Now you draw a line from the north pole to the plane, and it will cross the sphere through some point, and that point is being mapped onto the corresponding point in the plane. So this is how do we define this map. In fact, we will prove this. This is a geometric intuition, but we will prove this rigorously in this note. You can see that. Also, when x3 less than 0, this is the lower hemisphere, and x3 greater than 0, this is upper hemisphere. So via this map, the upper hemisphere is mapped onto the outside of the disk of radius 1. You can see that this is the disk of radius 1. So all the part in the upper hemisphere is mapped onto the outside part, and all the part in the lower hemisphere is mapped on the inside of this. That is geometrically evident. Once you draw a line from here to here, this is the case. But in fact, in this node, we proved this map. This is geometrically. I mean, we proved it analytically itself. There are some simple computations which you can see from here. So this S is called the Rayman sphere. Okay. Now we proved this. We use the line joining x, y, 0, x1, x2, x3, and 0, 0, 1. They are in the same line, and we proved everything analytically. So there is not. So these are all simple computations which you can easily follow. Now we proved a very important thing. Any circle on the sphere corresponding to a circle or straight line in the set plane. This is very important. Once we consider Mobius transformation, we know that they are conformal mapping from C infinity, means the extended complex plane into extended complex plane, and that maps circles into circles. There, the circle, by circle we mean circles or straight lines, right? So the reason is any circle in the sphere correspond to a circle or straight line in the Z plane. So let us prove this. So you know that a circle will on the sphere will, it is not a, it is a tilted circle now, because the circle is lying over the sphere. Now it is given by this equation. Now you can do some manipulation to assume that alpha 1 square plus alpha 2 square plus alpha 3 square equal to 1. That is simple. Otherwise you can divide by that. And this alpha naught, in fact, you can use the Cauchy-Schwarz inequality here to show that alpha naught will be lying between minus 1 and 1. And once it is, so by a simple multiple by scalar, you can assume that it is non-negative. But you can also prove that once alpha not equal to 1, you will have equality in the Schwarz inequality, where you will have linear dependence, and you will get that the corresponding set is only a singleton set, so that it will not represent a circle. So you can very assume that 0 less than or equal to alpha naught less than 1. Now, uh, now a simple computation will give you this. So this represents either a circle or a straight line. Once alpha naught equal to alpha 3, it represents a straight line. Otherwise, it's a circle. So that is one thing. Another important thing regarding stereographic projection is that distance in the Rayman sphere. So that's also you can compute. So what happens is that distance between z and z prime in the sphere, in the typical way, you compute it and you obtain this. dz z prime is equal to uh, this quantity 2 into mod z minus z prime divided by this quantity, and once z prime is infinity, this is this. So the thing is that you get a bounded matrix. So that's all from stereographic projection. Now let us consider the multivalued function. So that is another topic requested by a student. So how does a multivalued function arise? So the thing is that you recall the polar representation of a complex number. The quantity called argument comes into picture. What is an argument? Argument is basically the angle made by the number by the vector z with the positive real axis. But that is a multivalued thing. So